I've been calling this the Water Saver 2021, and its purpose is to use the Arduino to control this shutoff valve based on flow rates. In case my piping should ever break and I have a flow rate in excess of 40 liters a minute, or I have a slow leak anywhere from 0 to 5 liters a minute, hopefully this will kick in and shut the water off to the house. Here's the Water Saver 2021. Water comes in, goes through the shutoff valve, flow meter, up past the pressure transmitter and into the house. I have a bypass just in case this all fails and I'm not home and the kids can't figure it out. They can just open that up and get water back into the house. Here you can see the total volume used so far. The last cycle volume, that was probably a toilet for the 7.6 liters. The temperature in this room and the valve shut down in pressure. So VAL is the valve, and if the first one is a 1, then it was shut down on a high flow rate, or if it was a 1 over here, it's shut down on a low flow rate. And to reset this, if it does happen, you'll come down and you'll see on the board here that the red LED will be on. They'll have to reset the Arduino and then press and hold this button and it will open the valve back up. Here's somebody running the water. Definitely the bathtub at 32 liters a minute is what's going on here. Here's an example of doing less than 5 liters a minute. I just changed the time down to 30 seconds to show. Right now the valve is open, it's green, and the valve is closing. Water shut off to the house, and then you will see it display a low flow of 1 there. So that tells me what shut it down. So the valve is shut right now. To reset, gotta manually reset the board. Still showing that it's closed. Then I push my little button here, and that'll open it. And we are green to go. Here's some pictures of how this project came about. You can see it in place in my basement. You can see the cobweb of prototyping there. This is back up in my little project room where I'm taking it all apart and gonna make it into the nice PCB board. There's the blank on the left, and there's the completed on the right. Let's go over the design of the PCB here. I have 12 volts DC coming in, goes through the mini 360 DC to DC buck converter. The 12 volts comes right over through here, goes through the capacitor, goes into the L293 8-bridge motor drive chip, and in turn that supplies the 12 volts for both the open and closing of the motorized control shutoff valve. The 5 volts continues to the pressure transmitter, LCD screen, the flow meter, and I jumper it over to the L293 again, making it always enabled. The TMP36 uses the 3.3 volts coming off the NANO 33 IoT. I did make a mistake in my design here. For the ceramic capacitor, it should have been ground to the power, not ground to the signal out. So you can see I just filled in with some solder and I just jumpered from ground around the board to get to the power side that I needed. This is my voltage divider right here for the pressure transmitter, as the board can only read a maximum of 3.3 volt input. So I had to step it down. I did it 2 10K ohm resistors, making if this was at 5 volts, it would be 2.5 max. So that's more safe in the range that I need it. And I did bring in 2 pull down resistors here, so I don't have any stray current keeping it enabled. You can see I have some ceramic capacitors over here. That was just mentioned in the data sheet for the L293, so I went with it to cancel any noise. Welcome to my sketch. I'll walk you through it a bit. So you can see the first few lines I included the libraries that I needed. Some pin declarations. You'll see the flow sensor, the temp sensor, the pressure sensor, my motorized valve, pin declaration, as well as some variables. For the pressure and temperature readings, originally I was just using one analog read, and I just found it was just all over the place, the reading. Maybe I had some noise in my circuit, I'm not sure, but I decided to go with the smoothing sketch that's built into the Arduino examples, and I chose to do 20 readings and then take the average of that and smooth it. You can change those 20 to whatever you'd like. Then we'll continue on here, and you can see for Wi-Fi credentials you'll need to add your information. Very important, your API key. I used a 20 column 4 row LCD screen. You can change that if you've got something smaller or bigger. Some global variables. These are my ISR variables, the interrupt service routine. And if you click on that tab there, you can go into more details of why I chose them. Again, a few more variables throughout the sketch. Timing variables. Some of the very important ones was my high flow rate set for 4 minutes. My low flow rate I set for 10 minutes. And the update ThinkSpeak one I set for 5 minutes. Initializing the Wi-Fi client. Setting up my pin modes. Initializing serial begin, LCD screen begin, and the Wi-Fi begin. And then the Wi-Fi doing its connection. The interrupt that the water flow meter is attached to, I set it as a falling edge, and I never detach the ISR. I always leave it enabled. You'll see some sketches where people do have it disabled. I'm not sure why. I didn't see a reason to disable it, so I left it as is. And I'm using the external analog reference 3.3. You've seen in the PCB sketch there how I had it connected. Now let's get into the loop here. So right off the beginning here, I grab millis current times. I also have a variable set up to keep track of how long the sketch is continuously running, and that updates on the ThinkSpeak. I've set an if condition that at least 1 second needs to go by, and this interval here you can change up top there. And I found if I just continuously did the loop and it was less than 1 second, it would just drop the Wi-Fi connection for this NANO 33 IoT. Not sure why, but this solved my issue. Updating the current time. So here's where I get into the pressure reading, and I'm using all this to do a smoothing average. Come down here, and I have further explanation as to my formulas. You can see in the README tab up here as to why I did what I did. And we'll continue down. Same thing with the temperature reading. You can see the README file for further explanation as to why I did that as well. Now here's the meat and potatoes of this. So if pulse count is not equal to 0, meaning any pulse count reading higher than 0, then it starts running. So I calculate my liters per minute here, and this is displayed on the LCD screen. As I come down here, this is the beauty part of it. So if the flow rate exceeds 40 liters a minute and the interval time, which I have set for 4 minutes, then it will shut the valve. I have a low flow down here of 0.01 to 5 liters. If it does that value for 10 minutes, then it will shut the valve as well. Anything in between 5.1 liters to 39.99, it will reset the timer. It took a bit to find the range that worked best for our home. You know, every water fixture uses various amounts, flow volumes and stuff like that. There were hiccups, you know, the valve closing in the middle of showers and stuff like that, but growing pains, you'll need to adjust for your home. So if we go down, after it's done calculating all that, we go to the else statement here, and this new volume total takes the total flow divided by the 350, and that is the accumulated volume that is flowed through the flow meter, and that stays current unless you reset the panel. And then the cycle volume total to keep track of how much just happened in the last cycle of the flow meter moving. So in this example, the total, I suspect, at 7.65 liters. And then updating the previous values to carry forward through the loop, updating the time. This was a little bit of a catch-all I had to put in. I found the cycle volume total, if it was like if it was one pulse, it would just put it as 0.01. So by putting this 0.02 in, it alleviated that problem. And this is used for debugging purposes, just nice to see. This all prints out on the screen that you've seen in the previous part of this video. Resetting the pulse count going forward through the loop. Valve status, if the valve did close, this is where it would catch that status right now, and it would update into ThingSpeak going online, so I would know. So here's my ThingSpeak page. You can see the monthly volume used so far. We're up to roughly over 1,000 liters of a cube. Last volume usage, around 8:45, someone had a shower, roughly 62 liters. Water pressure, you can see it jumps all over. It's steady for 85 psi for some time. And then they must have turned the pump off in town here and then turned one back on. The room temperature, definitely much smoother using that smoothing average in the sketch. Before it was just all over the place. Valve status, 4 minutes ago, she was green, meaning the valve was open. Gauge pressure, see what it's at. Valve status, 0, meaning open. If it was closed, it would be a 1. Runtime, it's been running for continuously so far, or 35 hours. And pulse counts, that's what we're up to. It's pretty crazy how fast it climbs. So I can export this data to a spreadsheet at the end of the month and total the monthly volume used. If you reset the board in between, it goes back to 0, but you can use that data and summarize it. And I got pretty close for the month of May 2021. I estimated we used 15,500 liters, and the bill came in and it says we used 16 cubes, so I was off, you know, 500 liters. So that's not bad. I'm not looking for accounting purposes for this. I should mention too that you can get an app for Android or iPhone, and I can see this right on my phone anytime I want, these values of what's going on within the house. This is a breakdown of my cost. It was roughly 320 bucks Canadian. The biggest hit was the copper fittings, you know, the 3 isolation valves. They were like 18 bucks a piece. Unions, 90s, you know, all that stuff adds up. What would I do different? I don't think I would use the TMP36. I would use the DHT22. I've used them in other projects and I found them much more smoother for temp readings. I definitely wouldn't use the NANO 33 IoT. I probably should have went with the ESP32. Same analog inputs and, you know, a quarter the price. These LEDs, I wish I threw 5mm ones in there instead of the 3mm. I could change that out down the road. I wish I had a test button to test my valve that it would close just at a random time instead of hooking the laptop up to it and tripping it that way. And the L293 motor driver, I hardwired in the 5 volts directly, so it was 100% always enabled. I wish I ran another trace and just enabled it when I actually need it to close or open, and that way it's not always powered up. In the description you will find links to get the Arduino code, and this concludes the Water Saver 2021.